Most people imagine leaving the solar system as a gradual fading of the familiar into empty space. But the boundary is neither gradual nor empty. The edge of the sun's influence is called the heliosphere, a vast region inflated by the solar wind, a continuous stream of charged particles flowing outward from the sun. For billions of years, it has carved out a cavity in the surrounding galaxy, pushing against the interstellar medium and holding it at a distance. Not completely, but enough to matter. Inside this boundary space is still hostile but structured. The solar magnetic field dominates particle motion. Cosmic radiation is partially deflected, and the environment, though sparse, has a coherence shaped by one star. Then the structure ends. When Voyager 1 crossed this boundary in 2012, it did not drift into a softer vacuum. It encountered a measurable transition. Particle density increased, the magnetic field orientation shifted, and the background radiation environment changed in a way that confirmed something precise. The sun's domain is not infinite. It has an edge, and that edge is physically real. This boundary is not defined by distance alone. It is defined by pressure. The outward pressure of the solar wind balanced against the inward pressure of interstellar plasma and magnetic fields. Where those forces equalize, the heliosphere stops expanding. And beyond that point, the galaxy is no longer being pushed back. What lies just outside is the local interstellar cloud, a region of partially ionized gas through which our solar system is currently moving. It is not dense, it is not turbulent in any way we would recognize, but it is fundamentally different from the environment inside the heliosphere. The density is approximately 0.3 atoms per cubic centimeter, a number so small it resists intuition, and yet this is enough to define a new physical regime. This is the medium Voyager now travels through. This is the substance that fills the space between stars in our immediate neighborhood. The transition matters because it breaks a common assumption that space becomes progressively emptier the farther you go from Earth within the solar system. That approximation works. Beyond it, the assumption fails. There is no smooth gradient from something to nothing. There is instead a boundary between two different kinds of something. One shaped by a star and one shaped by the galaxy. And that shift introduces a constraint that is easy to miss at first. The moment you leave the heliosphere, you are no longer traveling through an extension of the solar system. You are moving through an environment that does not belong to it and does not respond to it. Which means any attempt to go farther is no longer just a question of distance, but of entering a medium that behaves by different rules. And those rules begin to matter immediately. And those rules begin with a property that is easy to state but difficult to comprehend: density. The local interstellar cloud surrounding the solar system contains on average about 0.3 atoms per cubic centimeter. This is not a rounding error or an abstract estimate. It is the measured environment through which the Voyager spacecraft are now moving. To understand what this means, it helps to compare it with something familiar. The air at sea level contains roughly 10 to the power of 19 molecules per cubic centimeter. The difference between these two numbers is not incremental. It is a gap so large that it collapses ordinary intuition about what emptiness actually is. Even the best vacuum chambers on Earth, engineered with extreme precision and effort, still contain millions of particles per cubic centimeter. They are considered near-perfect vacuums by laboratory standards, and yet they remain vastly denser than interstellar space. This leads to a counterintuitive conclusion. The space between the stars is not empty in the way we imagine emptiness. It is a medium, but one so diffuse that no direct human experience provides a reference point. And yet, despite this near absence of matter, the local interstellar cloud is not cold in the way we would expect. Its temperature ranges between 6000 and 8000 Kelvin, hotter than the surface of many stars. This seems contradictory until temperature is understood not as heat in a tangible sense, but as the average kinetic energy of particles. When there are so few particles present, the total energy contained in any given volume remains negligible, even if each individual particle is moving rapidly. The result is a state that does not exist anywhere on Earth, a gas that is simultaneously hot and effectively empty, a medium where thermal motion is high but thermal impact is almost non-existent. This introduces the first real shift in perspective. Leaving the heliosphere is not entering a colder or quieter region of space. It is entering a regime where familiar relationships between temperature, density, and energy no longer behave in intuitive ways. The composition of this medium adds another layer to that shift. Roughly 70 to 80% of the hydrogen remains neutral, while the rest is ionized, stripped of electrons by ultraviolet radiation from nearby stars. Along with helium and trace heavier elements, these particles form what astronomers classify as the warm, partially ionized medium. This is not just a passive background. It is a dynamic environment shaped by radiation, magnetic fields, and the long history of stellar activity in the region. And it exists within an even larger structure, the local bubble, a vast cavity carved by ancient supernova explosions that cleared out denser material millions of years ago, leaving behind a hot, low-density plasma that surrounds the cloud itself. So the solar system is not simply moving through empty space. It is passing through layers of structure, each one defined by processes that occurred long before the sun formed and that continue to influence the environment today. Which leads to a second shift in perspective. The interstellar medium is not a void between meaningful places. It is itself a product of astrophysical events, with its own history, its own structure, and its own constraints. And once that is understood, a new question begins to emerge. Not about how far the nearest stars are, but about what it actually means to travel through the space that lies between them. And once that is understood, a new question begins to emerge. Not about how far the nearest stars are, but about what it actually means to travel through the space that lies between them. Because even a medium this thin is not passive. At the velocities currently achieved by spacecraft like Voyager, the interstellar medium behaves almost as if it is not there. The particles are so sparse and the relative speed so modest that collisions are negligible, and the cumulative effect over decades remains small. But this changes the moment velocity increases. Any attempt to reach another star within a human timescale requires speeds that are no longer incremental improvements, but orders of magnitude higher on the scale of a significant fraction of the speed of light. And at those velocities, the same medium begins to behave differently. The key concept is ram pressure. The force exerted on an object moving through a fluid or gas, even when that gas is extraordinarily diffuse. The effect scales with velocity squared, which means that doubling the speed does not double the interaction, it multiplies it. At a fraction of light speed, the interstellar medium becomes something a spacecraft must push against continuously. Each individual atom carries momentum, and when encountered at extreme velocities, that momentum transfer becomes measurable over time. The medium does not stop the spacecraft, but it resists it, in a way that accumulates across light years, introducing a subtle but persistent drag that must be accounted for in any realistic mission design. This alone would be manageable, but the interstellar medium contains more than isolated atoms. Embedded within it are dust grains, microscopic particles composed of silicates and carbon-based materials, typically measuring fractions of a micrometer in size. At low speeds, these grains are harmless. Their mass is too small to matter and impacts are rare. At relativistic speeds, the situation changes completely. Kinetic energy increases with the square of velocity. And at 20% of the speed of light, even a grain smaller than a bacterium carries enough energy upon impact to damage or penetrate material structures that would otherwise be considered robust. A spacecraft moving at such speeds does not encounter dust. As occasional impacts, it experiences them as a continuous stream of high-energy collisions, each one small, but collectively capable of eroding surfaces, degrading instruments, and threatening the integrity of any exposed system. This introduces a constraint that is not immediately obvious from distance alone. The challenge of interstellar travel is not just reaching high speed, it is surviving that speed in an environment where even the smallest particles become hazards. And the faster the spacecraft moves, the more concentrated the problem becomes. Due to a relativistic effect known as forward beaming, from the spacecraft's frame of reference, incoming particles and radiation are increasingly compressed into a narrow cone in the direction of travel. Instead of arriving from all directions, the environment effectively focuses itself into the path ahead, intensifying both the frequency and energy of interactions in that direction. This transforms the geometry of the problem. The spacecraft is no longer moving through a uniform background. It is moving into a concentrated flux of matter and radiation that grows more intense with velocity, which leads to another shift in perspective. Speed is not simply a solution to distance. It is a variable that changes the nature of the environment itself. And this becomes even more significant when considering not just mechanical interactions, but radiation. Because the interstellar medium is not only composed of atoms and dust, it is permeated by a continuous flux of high-energy particles originating from distant astrophysical events. Particles that do not merely collide with a spacecraft, but pass through it, altering its internal structure at the smallest scales. And unlike dust, these particles cannot be avoided by orientation or shielding in any conventional sense. They are everywhere, and they do not behave like anything encountered within the protective boundary of the heliosphere. They are everywhere, and they do not behave like anything encountered within the protective boundary of the heliosphere. Beyond that boundary, the dominant hazard is not impact but penetration. The interstellar medium is filled with galactic cosmic rays. High-energy particles accelerated by events such as supernova explosions and propagating across the galaxy at velocities approaching the speed of light. They are not a localized phenomenon. They form a persistent background that exists everywhere between the stars. Within the heliosphere, this background is partially reduced. The solar magnetic field and solar wind act together to deflect a fraction of incoming particles, lowering the radiation intensity experienced by anything inside that boundary. Outside that protection, the full flux is present. The composition of these cosmic rays is simple at first glance. Most are protons, hydrogen nuclei, moving at extreme energies. A smaller fraction consists of helium nuclei, and an even smaller portion includes heavier elements such as carbon, oxygen, and iron. But simplicity in composition does not translate to simplicity in effect. When these particles encounter matter, they do not stop in the way ordinary projectiles do. A high-energy cosmic ray can pass through solid material, through electronic systems, through biological tissue, leaving behind a trail of ionization along its path. The damage from a single particle is small, but it is precise and cumulative. More importantly, the most significant effects are not caused by the primary particle itself, but by what happens when it interacts with atomic nuclei in the material it passes through. That interaction produces a cascade, secondary particles spreading outward from the point of collision. Neutrons, pions, gamma radiation, fragments of nuclei, all moving at high energies and depositing energy across a wider region than the original particle would have affected alone. This means that shielding becomes a paradox. Adding material does not simply block radiation, it can increase the number of secondary interactions within that material, amplifying the local dose in ways that are difficult to predict and control. For biological systems, this represents a fundamental limit. Exposure to the interstellar cosmic ray environment over extended periods would result in cumulative cellular damage at levels far beyond what is considered safe in any current space mission. Even within the heliosphere, astronauts on missions to Mars already approach lifetime radiation limits over the course of a few years. Beyond it, the dose rate increases further and remains constant for the entire duration of travel. For electronics, the challenge is different but no less critical. Each cosmic ray passing through a microelectronic circuit deposits charge along its path. If that path intersects with a memory cell or a transistor, it can change its state a bit. That was stored as 0 becomes 1. A calculation is altered, a control signal is corrupted. These events are known as single event effects, and while each individual occurrence is rare, the cumulative probability over long durations becomes significant. Modern electronics, with extremely small feature sizes, are particularly vulnerable. The smaller the components, the less charge is required to alter their state, and the more sensitive they become to passing radiation. This creates a tension in spacecraft design. High-performance systems require miniaturization, but long-term reliability in a radiation environment demands larger, more robust structures that are inherently less efficient. There is no straightforward solution to this trade-off. Active shielding using magnetic fields has been proposed. The idea is to recreate on a smaller scale the protective effect of the heliosphere, deflecting charged particles before they reach the spacecraft. But generating a magnetic field strong enough and large enough to provide meaningful protection requires energy and mass far beyond what current systems can deliver, especially for missions that must accelerate to extreme velocities. Which leads to another shift in perspective. The problem of interstellar travel is not only about propulsion, it is about maintaining functional integrity in an environment that continuously disrupts both biological and electronic systems at the smallest scales. And unlike many engineering challenges, this one does not diminish with distance. It remains constant from the moment the heliosphere is left until the destination is reached. There is no quieter region, no natural shelter, no gradual easing of conditions. Only a steady exposure to a background that has existed for millions of years, shaped by events occurring across the galaxy and indifferent to anything attempting to cross it. And this raises a deeper constraint, one that is not immediately technical but operational. Because surviving the environment is not enough. A spacecraft must also function within it, make decisions within it, and remain coherent over timescales that extend far beyond any direct human control. Which means the challenge is no longer just about withstanding the interstellar medium, but about operating inside it without intervention and without immediate connection to the place it came from. Which means the challenge is no longer just about withstanding the interstellar medium, but about operating inside it without intervention and without immediate connection to the place it came from. Because distance in interstellar space does not only separate locations, it separates time. Communication across that distance is constrained by a constant that cannot be engineered around: the speed of light. Even at the relatively small scale of the outer solar system, this delay is already significant. Signals from Voyager 1 take more than 20 hours to reach Earth, and another 20 hours for a response to return. At interstellar distances, this delay expands beyond operational relevance. A spacecraft traveling toward the nearest star at a distance of just over 4 light years would experience a minimum one-way communication delay measured in years. Any instruction sent from Earth would arrive long after the situation that required it has changed, and any data returned would describe conditions that no longer exist. This eliminates a fundamental assumption underlying all previous space exploration, that real-time or near real-time control is possible. Instead, the spacecraft must operate as an autonomous system, not in a limited sense, but completely. It must detect anomalies, interpret them, and respond without external input. It must prioritize scientific observations, manage its own resources, and maintain its own functionality across decades or longer. Autonomy at this level is not simply an extension of current technology. It is a qualitative shift in how missions are conceived. The spacecraft is no longer a remote instrument. It becomes an independent agent executing a mission that cannot be supervised in any conventional sense. Navigation introduces a related complication. Within the solar system, spacecraft positions are determined with high precision using radio tracking and the predictable gravitational influence of the Sun and planets. This framework provides a stable reference against which motion can be calculated. Beyond the heliosphere, that reference weakens. The spacecraft can still be tracked relative to the solar system, but navigating toward a distant star requires predicting the motion of both the spacecraft and the target over decades, accounting for uncertainties that accumulate over time. Stars themselves are not fixed points. They move through the galaxy, each with its own velocity and trajectory. The position of a target system must be projected forward with extreme accuracy, because even a small error at the start becomes a large deviation after traveling for years at high speed. At relativistic velocities, additional effects begin to matter. Interactions with the interstellar medium, though weak on short timescales, accumulate into measurable deviations. The spacecraft does not move through a perfect vacuum. It moves through a medium that exerts pressure, however slight. And over light years, that pressure alters its path. Correcting for these deviations requires onboard systems capable of continuous measurement and adjustment without waiting for instructions, which leads to another shift in perspective. Interstellar navigation is not about aiming at a destination. It is about continuously redefining the path in response to an environment that cannot be fully predicted in advance. Even communication itself becomes part of the constraint. Transmitting data across light years requires energy, precise alignment, and time. The signal weakens with distance, spreading out as it travels until it becomes indistinguishable from background noise, unless it is carefully encoded and detected. The larger the distance, the more limited the data rate becomes. A spacecraft may collect vast amounts of information, but only transmit a fraction of it back to Earth, forcing decisions about what is worth sending and what must be discarded. This transforms the mission from one of exploration to one of selection. The spacecraft must choose which observations justify the cost of transmission, which measurements carry enough value to cross years of empty space as faint signals. And this introduces a final operational constraint, the mission timeline itself. At velocities achievable today, reaching even the nearest star would take tens of thousands of years, far beyond the lifespan of any human system of organization or continuity. Even at theoretical higher speeds that reduce travel time to decades, the mission still spans generations of technology development on Earth, during which the systems that launched a spacecraft may no longer exist in their original form. The spacecraft becomes a message sent into the future, not only across space, but across time. And once that message is sent, it cannot be revised in response to what is learned along the way, which reframes the nature of interstellar travel entirely. It is not an extension of exploration as we currently understand it, but a commitment to act without feedback, to move forward without the ability to adjust based on immediate knowledge. And in that sense, the greatest distance between stars may not be measured in light years, but in the separation between action and response, between what is done and when its consequences can finally be understood. A separation that grows with every kilometer traveled outward and does not close again until the journey is already over. Or perhaps until something arrives at the other side and begins to send a signal back across a distance that still cannot be crossed in time to matter. A separation that grows with every kilometer traveled outward and does not close again until the journey is already over. Or perhaps until something arrives at the other side and begins to send a signal back across a distance that still cannot be crossed in time to matter. And this is where distance itself stops being a number and becomes a physical constraint that reshapes understanding. Because the nearest star is not just far, it is separated by a scale that the human brain was never designed to process. A light year is often defined as the distance light travels in 1 year. But that definition remains abstract until it is translated into something cumulative, something that unfolds over time rather than being stated as a static figure. Light moves at approximately 300,000 kilometers per second. In 1 second, it travels a distance greater than the circumference of Earth 7 times. In 1 minute, it crosses the space between Earth and the Moon multiple times. In 1 hour, it spans distances that exceed the entire orbit of the Moon by orders of magnitude. and it continues without interruption for an entire year. The result is a distance so large that writing it down does not clarify it. 5.9 trillion miles, or about 9.5 trillion kilometers. And this is only one light year. The nearest star system lies more than 4 of these units away, meaning that even light requires over 4 years to make the crossing. Nothing physical can move faster than this, and anything slower extends that timescale accordingly. At the velocity of Voyager 1, the fastest sustained speed ever achieved by a human-made object, the journey would take tens of thousands of years. This is not a technological inconvenience. It is a mismatch between the scale of human systems and the scale of interstellar space. Civilizations do not operate on these timescales. Institutions do not persist with continuity across them. And technologies do not remain static long enough to complete such a journey without becoming obsolete long before arrival. This introduces a shift that is more conceptual than technical. The challenge of interstellar travel is not only about crossing space, it is about bridging a gap between the duration of the journey and the lifespan of the systems that initiate it. Even attempts to reduce this gap through theoretical high-velocity propulsion reveal a different limitation. At a significant fraction of the speed of light, the journey time may compress to decades, but the environment, as previously described, becomes increasingly hostile. Dust impacts intensify, radiation exposure increases, and navigation becomes more complex. Speed solves one problem while amplifying others, which leads to an important reframing. The distance between stars is not a passive separation waiting to be crossed. It is an active filter that selects for what kinds of systems can survive the journey at all. Biological organisms with finite lifespans are constrained by time. Mechanical systems are constrained by durability, and information systems are constrained by both radiation and delay. No single approach resolves all of these simultaneously, and yet the scale becomes clearer when translated into proportion rather than absolute numbers. If the distance between the Earth and the Sun is reduced to a single millimeter, then the entire solar system fits within a region small enough to hold in one hand. The boundary of the heliosphere sits only a few centimeters away. On that same scale, the nearest star lies hundreds of meters distant, far beyond the immediate surroundings, separated not by a small extension of space, but by an expanse that dwarfs the system itself. This comparison reveals something that raw numbers obscure. The solar system is not a large structure within the galaxy. It is a small, localized region embedded in a much larger volume that it does not influence. And the space between stars is not a narrow gap. It is the dominant component of the galaxy's structure, which leads to a final shift in this progression, the realization that interstellar space is not defined by what it lacks, but by what it enforces. It enforces isolation between stellar systems. It enforces delays between cause and effect. It enforces constraints on motion, energy, and survival that cannot be ignored or bypassed. And once those constraints are recognized, the question changes again. Not how far the nearest star is, but what kind of system could exist that is capable of crossing that distance without being limited by the same boundaries that define it. Not how far the nearest star is, but what kind of system could exist that is capable of crossing that distance without being limited by the same boundaries that define it. Because the structure of the galaxy does not resemble a continuous environment. It resembles separation. Each star generates its own region of influence, an astrosphere. shaped by stellar wind and magnetic fields, carving out a localized cavity in the interstellar medium, similar in principle to the heliosphere surrounding the Sun. Within these monadid, conditions are modified. Radiation is partially reduced, particle flows are organized, and the environment becomes marginally more stable for complex structures to persist. But these monadid do not connect. They exist as isolated domains embedded within a much larger volume of unmodified interstellar space. The distance between them is not filled with transitional gradients or protective corridors. It is filled with the same medium that Voyager now measures, a diffuse plasma, threaded by magnetic fields, permeated by cosmic radiation, and largely indifferent to the presence of anything moving through it. This introduces a structural reality that is easy to overlook. The galaxy is not a network of reachable systems. It is a collection of islands separated by an ocean that does not facilitate travel between them. The heliosphere itself illustrates this asymmetry. Its diameter is approximately a fraction of a light year, while the distance to the nearest star exceeds 4 light years. The protective region generated by the Sun occupies only a tiny fraction of the space between stellar systems. Everything beyond that fraction is exposed to the baseline conditions of the galaxy. And this exposure is continuous. There is no region between stars where the environment becomes neutral or benign. The interstellar medium does not provide staging areas or intermediate zones of reduced constraint. It maintains its properties across vast distances with only gradual variations in density and structure. Even within the same local interstellar cloud, the conditions remain broadly consistent from one stellar neighborhood to another. This means that any system attempting to travel between stars must carry with it everything required for survival, operation, and adaptation, because nothing external will provide assistance or relief along the way. The journey is not supported by the medium, it is resisted by it. Which leads to another shift in perspective. The difficulty of interstellar travel is not concentrated at the beginning or the end of the journey. It is distributed across its entire duration. There is no phase where the environment becomes easier, no midpoint where constraints relax, no final approach where external conditions improve before arrival. Instead, the system must remain functional under constant exposure for the entire transit. And this continuity introduces a deeper implication about the nature of exploration at this scale. Within the solar system, exploration is incremental. Missions build on previous knowledge, adjustments are made based on feedback and the environment, while harsh remains within a range that can be modeled and managed with increasing precision. Beyond the heliosphere, that framework breaks down. The environment remains measurable, but it does not become more accommodating. With understanding, knowledge does not reduce the fundamental constraints, it only clarifies them. And this creates a distinction between knowing and being able to act on that knowledge. We understand the properties of the interstellar medium with increasing accuracy. We can measure its density, its temperature, its magnetic structure, and its radiation environment. But that understanding does not translate into immediate capability to traverse it, which introduces a tension that sits at the center of the problem. The more precisely the environment is characterized, the more clearly its constraints are defined, and the more evident it becomes that those constraints are not easily overcome by incremental advances. They require changes in approach that may not align with current technological trajectories. And this raises a question that extends beyond engineering. If the galaxy is structured as a collection of isolated systems, separated by a medium that resists traversal, then the absence of interaction between those systems may not be a temporary limitation, but a persistent condition. Not because travel is impossible, but because the cost of crossing the interstellar medium may remain high enough that it is rarely undertaken, which leaves an unresolved tension between what can be measured and what can be achieved. We can observe neighboring stars, detect planets around them, infer their properties, and model their environments with increasing detail. But the medium that separates us from them remains the same: measured space that Voyager has entered, unchanged across the distance, unresponsive to intention, and still extending outward in every direction beyond the reach of any system that has yet demonstrated the ability to cross it in a way that meaningfully closes that distance. Which suggests that the boundary we crossed with Voyager was not only the edge of the solar system, but the beginning of a region that may define the limits of how far any system like ours can extend before something more fundamental has to change or something else has to be sent instead. Which suggests that the boundary we crossed with Voyager was not only the edge of the solar system, but the beginning of a region that may define the limits of how far any system like ours can extend before something more fundamental has to change, or something else has to be sent instead. Because the question is no longer whether something can cross the interstellar medium, but what kind of thing can do so without being constrained by the same limits that define it. Biological systems are bounded by time. Even under ideal conditions, human lifespans are short compared to interstellar travel durations. And extending those lifespans introduces new dependencies on stability, environment, and protection that the interstellar medium does not provide. Mechanical systems are bounded by durability. Every component degrades. Materials fatigue, electronics accumulate damage, and redundancy can only delay failure, not eliminate it. Especially in an environment where repair cannot be performed externally and intervention is delayed beyond relevance. Information systems appear to offer a different pathway. Data can persist independently of a specific physical form. It can be copied, transmitted, and reconstructed. In principle, this allows a shift from transporting matter to transporting patterns, from moving bodies to moving descriptions. But even this abstraction encounters the same constraints. Transmission is limited by the speed of light. Storage is limited by physical media. And reconstruction requires a receiving system capable of interpreting and instantiating the information that arrives. The medium does not disappear simply